video where we prove a very interesting formula about the computation of determinants. This formula ultimately goes on to prove that the determinant function exists for every single dimension of matrix over any given field that has non-zero, that has zero characteristic. In particular, it exists for real matrices of dimension n for any given n. This formula is commonly referred to as the Lagrange formula for determinants. We also show then later on that in another part of the video we show that the determinant function is multiplicative. So the following theorem will prove the existence of the determinant function on Mn of R, that is the space of real matrices over R with dimension n. So let D be an alternating n linear function on Mn minus 1 R for n greater than 1 and for jk, two indices in the string list 1 to n. We define the function djk evaluated at A to be the determinant of the augmented matrix A by deleting row j and column k. That's what we denote as A brackets j bar k. And this is for any matrix A in the set of real matrices over R. Now, for any k in the index list of 1 to n, the function ek of A is defined to be the sum as j goes from 1 to n of minus 1 to the power j plus k times the product of ajk djk evaluated at A. So this is a linear combination of this product ajk djk. Ajk here simply stands for the scalar entry in row j and column k of the matrix A. It's simply a scalar valued function, while djk here represents the function that we just defined for real matrices over Mn. So if the function d is alternating and n-linear, then so too is also ek. Ek will also be alternating and n-linear. Further, if d is a determinant, then so too is ek. We now go on to prove this result. This result has to be proven in 3 steps. We need to prove one, that the function ek is n-linear. Then we need to prove it's alternating. And lastly, we need to prove that it is a determinant if d is a determinant function on matrices of dimension n minus 1. This way, this allows us to complete the induction step. And we already know that we can define determinants on matrices of dimension 1. And this allows us to grow that definition for any given matrix dimension. So for indices j and k in the index list of 1 to n, denote by alpha j the vector in row j of the matrix A. The function ajk evaluated at alpha j given by alpha j sub k, meaning the kth entry in the row vector alpha j, is an n-linear function on row vectors of length n. Further, the function djk is an alternating n minus 1 linear function on the rows of A, excluding alpha j. and it is independent of the row alpha j because in the definition of djk, one needs to delete row j and column k from the matrix A. So indeed, now if we hold the other rows fixed and simply alter row S of the matrix A, and we do that by taking a linear combination of vectors alpha S and beta S in row S as C alpha S plus beta S, and we evaluate Ek on this new matrix with just the row S altered, all other rows being held fixed. We now compute the matrix. We compute the value of Ek using the definition. So we need to split this into two cases. One case is where the index j in our sum is different from S, and one where it is equal to S. So in the case where it is different from S, we have a straightforward application of the definition. We simply write it as ajk djk with the scalar coefficients of -1 to the power j plus k, and that's evaluated as C alpha S plus beta S. But when the index j is equal to S, then we need to substitute j in this definition here with S and make simplifications as necessary. So the first is that we get -1 to the power S plus k. Next, we see that we have dsk evaluated at A. Here there is no need to make reference to the row vector S, row vector at S, because in the definition of dsk, one needs to delete row S and column K, so that no longer exists. The other rows of A stay as they are for dsk. But in the scalar coefficient ask, what one needs to do ultimately is to substitute alpha C alpha S plus beta S. But here we are simply finding or picking out the case entry in row S of the new matrix A. We already know what row A consists of, that is C alpha S plus beta S. And then picking out the case entry is a linear operation. So that is just going to distribute over C alpha S plus beta S in the normal way that linear transformations do, or linear functions do. We now go to the next step of our equality and try to simplify the sum. We do not make any adjustments to the first part of the sum where the index j is equal to S, but we do make adjustments to the second one, or simplifications. Here what we need to do is we notice that djk evaluated as C alpha S plus beta S will also be linear, and that will be linear now because D itself is n linear, and now in this case, since the index j is different from S, the row S does in fact incorporate C alpha S plus beta S, and it can no longer be ignored. So now djk needs to distribute over row S as C djk at alpha S plus djk at beta S with the coefficient of -1 to the power j plus k at the front as before. This now simplifies from before as two different sums. We combine the terms that are multiplied by the coefficient C together, and then we combine the terms evaluated at beta S together and group like terms that way. We combine over all indices now. Once again, we do not distinguish between indices of j. So we take the sum as j goes from 1 to n with the scalar coefficient C out front, and that is evaluated at alpha S. The terms are ajk djk with the coefficient of -1 to the power j plus k, and we've got the second sum of ajk djk evaluated at beta S with the coefficient of -1 to the power j plus k. Again, This is a simple linear combination of two different terms. We already recognize each of these terms. This is the function ek evaluated at alpha s, and this here is the function ek evaluated at beta s. So it follows that ek is n-linear. Now it comes down to proving that ek is alternating. So suppose that the rows alpha s and alpha t for distinct s and t in the index list of 1 to n are equal. So notice first that when j is not equal to s or t, we have the djk evaluated at a vanishes. And that is because in that case, the augmented matrix A j bar k does in fact have two equal rows, namely the row alpha s and the row alpha t. They might not be at positions j and alpha s and row alpha t. They may not be at positions positions s and t because of the presence of j and the deletion of row j. So if row j lies before rows s and t, then both s and t are going to reduce and come up a step 1. And there'll be other cases if j lies in the middle of s and t, or if j lies beyond s and t, in which case there is no change to the index j and s in this index of s and t. So now we can simply assume that s is less than t, and look at the remaining terms in the definition of ek in our sum, and that's just two terms. It's just the case where j is equal to s separately and the case where j is equal to t separately. So for each of those terms we have minus 1 to the power s plus k. This is for s, where j equals s. We have ask, dsk, alpha t, and we have the term where j is equal to t. So that's minus 1 to the power t plus k. That corresponds to atk and dtk, again evaluated as alpha s. Now note that dsk evaluated at alpha t is simply given as a product a product of dtk at alpha s because multiplied by negative 1 to the power t minus s minus 1. Let me explain this. So dsk at alpha t and dtk at alpha s are both determinant functions on very similar matrices. The only difference in the two cases with A adjusted for at sk is that we delete row s and we have row t still remaining, which consists of alpha t, while in dtk we've deleted row t and the row alpha s still remains. So in both of these cases, the matrices have exactly the same rows because we note that alpha s is equal to alpha t, but the positions of alpha s and alpha t are different. In dsk, the position of alpha t is at row t, and the position of alpha s in dtk is at row s. So we realize that the number of transpositions that we will need to get to change the matrix for the computation dtk alpha s into the matrix for dsk alpha t is simply to shift the row alpha s down, or rather, I mean, we shift the row alpha t down excuse me, we shift the row alpha s down by t minus s minus 1 steps to get the position of t minus 1, because now we know that j, we suppose, um, we know that s is less than t, and so if we are deleting row s in the matrix A, what's going to happen is that now row alpha t does not occupy position t or row t, it occupies row t minus 1 or position t minus 1. And that is why we have this exponent of minus 1 to the t minus 1 minus s. That's the distance between the two rows, alpha t and alpha s, in these two different matrices. Remember, all other rows are the same and they're unchanged. So that's the only difference here now. And we also note that ask is equal to atk, because again, the s row and the t row are identical, so too must their kth entries be identical. So we calculate that ek is now equal to the following sum. It's equal to dtk at alpha s multiple times a particular sum. So we are first substituting dsk at alpha t by the formula minus 1 to the power t minus s minus 1 and dtk at alpha s. We factor out dtk alpha s. We have the factor of minus 1 to the power t minus s minus 1, which comes here. And we've got the original factor of minus 1 to the power s plus k, which came from here. We of course have ask, not to forget. And now in the second half of the sum, we have simply minus 1 to the power t plus k and atk as before. dtk alpha s is factored out just as before, so there's nothing to consider. Now we recognize that this product of the two coefficients or the two exponents of minus 1, we simply add the exponents s plus k plus t minus s minus 1. And when we add the coefficient, we add the exponents, what we get is t plus k minus 1 as an exponent on minus 1 times ask as before, and the second half stays the same, minus 1 to the power t plus k times atk. But we know that ask is equal to atk, and these two coefficients are almost identical, but for the difference of minus 1 over here. That means these two sums are going to cancel each other out, or these two terms are going to cancel each other out, because if this is positive, if minus 1 to the power t plus k minus 1 is positive, then minus 1 to the power t plus k must be negative, and vice versa. Finally, now it is time to prove that ek maps the identity to itself, if D does so too. So this here is very straightforward. Indeed, if j is not equal to k, we see that djk at 1 is equal to 0. And this can be reasoned through as follows. Without loss of generality, suppose that there's an index r lying in between j and k strictly. Then we see that r may also be equal to 1 of j or k, but that's not going to change the argument very much. Then we see that the entry at the position r comma r of the augmented matrix A j bar k is nothing but A sub r plus 1 comma r, and that is 0, because we are considering A to be the identity matrix 1, and we know that the identity matrix 1 has the entry at r plus 1 comma r to be equal to 0. Further, we also know that in the augmented matrix AJK, when we delete row J and we delete row column K, what essentially happens is that all the ones in the diagonal lying between j and k will now get shifted up one space. All other diagonal entries will be 1, but the diagonal entries lying between indices j and k will actually get shifted up by one space, and hence we have a lot of zeros in the diagonal. Notice that if j is just 1 less than k, then 2, what's going to happen is that the diagonal entries will all be 1 except for a single entry of 0 at the diagonal entry k comma k, because that entry is what's going to get that one is going to end up getting deleted in the new augmented matrix. So we immediately have that all other terms in the definition of ek evaluated at 1 will cancel, but for the sum at index j equal to k. And when we substitute j equal to k in our definition for ek over here as before, what we get is minus 1 to the power 2k times a k bk evaluated at the identity matrix 1. But bk evaluated at the identity matrix 1 is nothing but 1, and so too ak evaluated at the identity matrix 1 is the kth entry on the diagonal of the identity matrix 1. That is also 1, and minus 1 to the power 2k is minus 1, is negative 1 to an even power, which again is 1, is again positive. So we conclude that ek of 1 is equal to 1. And that brings us to the end of this proof, that ek is also a determinant function if the function D is. Thank you for watching, and please stay tuned for the next video where we show that the determinant function is multiplicative. As a quick little corollary, we have the following result. The determinant function exists for all given n. Since we now have a way to construct a determinant function on the space of real matrices of dimension n, given that we already have one on m minus on real matrices of dimension n minus 1 for n greater than 1. Indeed, the function d of x equal to x for scalars x in the field f is a well-defined determinant function on K1, and that is alternating, it's n-linear, it's one-linear in fact, and it sends the identity that is 1 to itself. So using this formula, using the formula we've just established, we can calculate E1 on the space K2 by 2, that is the space of real matrices of dimension 2. We then have that E1 of A is equal to minus 1 to the power j plus 1 times aj1 dj1 evaluated at A. The sum of indices goes from j equals 1 to 2, and that simplifies to nothing but A11, A22, because we recall that D11 evaluated at A is equal to A22. We simply delete row 1 and column 1, and all we're left with is the scalar A22. Similarly, for D21, we need to delete row 2 and column 1, and then all we're left with is the scalar in row 1 and column 2, which is A12. So what we have is the difference between A11 times A22 minus A12 times to A21. And the determinant function must exist then by induction, because now we've found a determinant function E1 on K2. We can then find one on K3, then on K4, then on K5, and so on ad infinitum. This shows that the determinant function must exist.